Hello everyone, my name is Innocent and you are watching Innotutorial. In this lesson, we are going to draw shear and bending moment diagram of a beam. So this is going to be a part 2 of drawing shear and bending moment diagram. If you've not watched part 1, try to watch part 1 by clicking the card on this video. Also, if this is the first time you are coming across my channel, and if you are interested in civil engineering tutorials, do not hesitate to subscribe to this channel by clicking the red subscribe button, because I make videos about civil engineering. So do not hesitate to subscribe to the channel if you are interested in civil engineering tutorials. With that being said, let's draw shear and bending moment diagram of a beam. So as you can see on the screen, we have a beam. And on this beam, we have a pin support and we have a roller support. So let's call this A and let's call this B. So we have a pin support and a roller support. So meaning we are going to have 3 unknown reactions, because for pin support we have 2 unknown reactions, while for roller support we have 1 unknown reaction. And the load acting on the beam, we are having a distributed load of 5 kilonewton per meter. So this is acting on the beam, and this is constant throughout the length of the beam, and the length of the beam is 3 meters. So we need to draw the shear and moment diagram for this beam. So the first thing you need to do when you want to draw shear and bending moment diagram, you first need to calculate the support reactions. So this is the first step you need to take when drawing shear and bending moment diagram. So let's first of all calculate the support reactions. So at point A, which is the pin support, we are going to have an unknown vertical reaction. So let's call this AY. Then we're also going to have an unknown horizontal reaction, which is AS. Then at point B, which is the roller support, we are going to have an unknown vertical reaction, which is BY. So we're going to have just one unknown reaction because that is a roller support. So we are always going to assume the direction of the reaction to be acting upward. If we have a positive value, that is after calculating the support reaction, if we have a positive value, meaning our assumption is right. But if we have a negative value, meaning our assumption is wrong, this is acting in the opposite direction, which is downward. Then also for the horizontal reaction, we are going to assume this is moving to the right. So if you have a positive value, it is correct. If you have a negative value, it is wrong. It is moving in the opposite direction. So let's first of all calculate for these reactions. Now, as you can see, we don't have any horizontal reaction, that is, we don't have any horizontal force in this beam. So because we don't have any horizontal force in this beam, so meaning AS is automatically going to be equal to 0 because we don't have any horizontal force. So let's say AS is equal to 0. So now we are left with just AY and BY. So let's calculate for BY. So to calculate for BY, we are going to take summation of moment at point A, which is summation of moment at the pin support, equals to 0. So we're going to say summation of the moment at point A is equals to 0. And we're going to make an assumption. We're going to say all the movement in the counterclockwise direction should be positive, while all the movement in the clockwise direction should be negative. So take note of that. You can also say all the movement in the clockwise direction should be negative, but this is just the way I like to calculate the support reaction. So I'm saying all the movement in the clockwise, all the movement in the counterclockwise direction should be positive, while all the movement in the clockwise direction should be negative. So if I'm taking a moment at point A, if I apply a force BY acting upward with relative to the point A, it is going to try to rotate this beam in the counterclockwise direction. So meaning it is going to be a positive value. And because we want to calculate for the moment, and we know that moment is equals to force times distance, so it's going to be this force BY. So we're going to have BY then multiply by the distance. So the distance, as you can see over here, is 3 meters. That is the distance from the roller support to the pin support. So that is 3 multiply BY. So that is 3 meters multiply BY. So now, as you can see over here, we have a distributed load of 5 kilonewton per meter. So whenever you have a distributed load, you need to decompose this load into its resultant. So to decompose the load into its resultant, you just need to take the area So it is going to be the height of this, the height then multiplied by the breadth. So it's going to be 5 kilonewton per meter then multiplied by 3 meters, because this is distributed over a length of 3 meters. So you need to multiply 5 kilonewton per meter by the length. So this is going to give us a 15 kilonewton, because the meters are going to cancel out. So this is going to be at the middle, because this is a rectangle, so it's going to be at the middle. So the resultant force is going to be acting at the middle, which is 15 kilonewton. So this is the resultant force. So now we have the resultant force. We are going to take the moment from point A. So the 50 kilonewton is going to be acting on the beam, and we need to take the moment. So the moment is going to be 50 kilonewton then multiply by the distance from 50 kilonewton to the point A, which is going to be 1.5 meter. So if we apply 50 kilonewton with relative to the point A, it is going to try to rotate this beam in the clockwise direction. So it is going to be a negative value. So this is negative 15 kilonewton then multiply by 1.5 meters. So we don't have any additional force, because AY is acting at point A, and this is where we are taking the moment at. So it is not going to produce any moment, because there is no distance. Because there is no distance, then there will be no moment produced. So we don't have any additional force, so this is equals to 0. So all you need to do, you just need to solve for BY. So right now it is very easy. You just need to calculate for BY using your calculator. So BY, if you solve for BY, you are going to get BY is equals to 7.5 kilonewton. So this is the value of BY, 7.5 kilonewton. So now we know BY. Let's calculate for AY. To calculate for AY, you just need to take summation of all the forces in the vertical direction so that you can calculate for AY. So we're going to take summation of all the forces in the vertical direction is equals to 0. And I'm going to assume all the forces acting upward should be positive, while all the forces acting downward should be negative. As you can see over here, BY is positive. As you can see, we're having a positive value. So meaning our assumption is indeed correct. BY is indeed acting upward. At the B we have negative. If we have negative value, meaning our assumption is wrong, BY is acting downward. So because we're having a positive value, our assumption is right, BY is acting upward. So let's do the same here. So we're going to take summation of all the forces in the y direction is equal to 0, and all the forces acting upward is positive, while the forces acting downward is negative. So as you can see, BY is acting upward, which is 7.5 kilonewton. So this is 7.5 kilonewton. Then we have 15 kilonewton. This is acting downward, so it's going to be negative. So this is negative 15 kilonewton. Then we have the force AY, which we want to calculate, and this is acting upward, so this is going to be positive AY. Then this is equals to 0. So 7.5 minus 15, so this is going to give us negative 7.5. So if we move this to the right side, we are going to get AY is equal to 7.5 kilonewton. So we are having the same value for AY and BY, because we're looking at this. If we are applying a load of 15 kilonewton, the resultant, they need to cancel out the force. So if we have 7.5 kilonewton as BY, then definitely AY should also be 7.5 kilonewton, so as to cancel out the force acting on the beam. So now we have these values, we are ready to draw our shear and bending moment diagram. So let's write these values here. So AY is equal to 7.5 kilonewton. Then BY, this is equals to 7.5 kilonewton as well. So now we are ready to draw our shear and bending moment diagram. So to draw your shear and bending moment diagram, you need to draw a vertical line wherever you see any reactions. So wherever there are reactions, you draw a vertical line, and also wherever there are discontinuities, you draw a vertical line, and wherever there are load, you also draw a vertical line. So as you can see, we are going to draw our vertical line starting from the pin support. So let's draw one vertical line here. Then we're also going to draw another vertical line on the roller support. So we don't have any discontinuity here. So this is going to be our two vertical lines. So the first one is usually the shear diagram. So we're going to draw an horizontal line here. So this is going to represent the shear diagram. So this is V in kilonewton. So the next one is going to be the moment diagram, but let's first of all draw the shear diagram. So now, if you take a look at this, whenever you want to draw a shear diagram, you need to start from the left side, then you need to move to the right side. And also, when drawing your shear diagram, your values, your area need to close up. So take note of that. So now, let's take a look at this from the left side. So from the left side, we have AY is equal to 7.5 kilonewton, and this force is acting upward. So meaning we are going to move 7.5 kilonewton upward. So this is how you do it. You start from the left, you take a look at the support reaction. So because we don't have any horizontal reaction here, so we don't bother about that. So we just take a look at the vertical reaction. So we're having 7.5 kilonewton, and this is acting upward. So meaning we are going to move 7.5 kilonewton upward. So take note of that. So it's going to be somewhere here. So this is 7.5 kilonewton. So this is 7.5 kilonewton. So now we are at 7.5 kilonewton. So we need to move to the next part. So after we have 7.5 kilonewton, when you take a look at this, what do we see next? We see a distributed load of 5 kilonewton per meter. So this is what you are going to do in order to make it very, very easy, in order to simplify your work and in order not to make any mistake. You are going to say 7.5 kilonewton, right? We started from 7.5 kilonewton, then plus we have a distributed load. So we are going to draw a distributed load. So this is a distributed load we have. So we have a distributed load of 5 kilonewton per meter. So now we need to take a look at this. So if we have a distributed load of 5 kilonewton per meter, so what we are going to do is we need to take the area of this distributed, that is the area of this rectangle. I will know the length. The length is basically 3 meters. So it is going to be 5 multiplied 3, which is going to give us 15 kilonewton. So, and because this is acting downward, meaning it is going to be a negative value. So it's going to be 7.5 then minus 15 kilonewton. So it's 7.5 kilonewton minus 15 kilonewton, which is going to give us, this is going to give us negative 7.5 kilonewton. So we now have negative 7.5 kilonewton. So we are going to take a look at the diagram here. So where can we locate 7.5 kilonewton? So 7.5 kilonewton can be located somewhere here, because this is going to be below the neutral axis, that is below the zero. So this is going to be 7.5 kilonewton. So this is negative 7.5 kilonewton. So now all we need to do, we just need to connect this the first value to the next value. And as you can see, because we're having a constant slope, as you can see, we're having a constant slope. As we move from left to right, the slope is not changing, it is constant. So all we need to do, we just need to connect this. We just need to connect these two values because they are constant. So we're going to have something like this because they are constant. So the slope is constant. So this is going to be the shear diagram for this beam. So as you can see over here, we have a positive area, and over here we have a negative area. So now we are done with the shear diagram. So now we can draw the moment diagram. So to draw the moment diagram, first of all, you need to draw a vertical line here. Sorry, an horizontal line. So this is moment, and this is m. It is in kilonewton meter because moment is force times distance. So now let's draw the moment. To draw the moment diagram, you need to take the area of the shear diagram. This is how you draw the moment diagram. You take the area of the shear diagram. So now let's take a look at the shear diagram. This is the shear diagram, right? So we are going to take a look at this area and also this area. So we are going to take a look at the positive area. We're also going to take a look at the negative area. So meaning we need to take the area of this triangle. We also need to take the area of this triangle. And we know that the area of a triangle is length times breadth, then divided by 2. So we need this distance. We don't know this distance. We don't know the distance, but we know that the total distance is 3 meters. So let me draw this so that you can see this clearly. So we have something like this. I have something like this. Okay, so we know that the total distance, this distance is 3 meters. So we know that this distance is 3 meters, but we don't know this distance, so we're going to call this distance S, and if this distance is S, then meaning this other distance is going to be 3 minus S. And we know that the height of this triangle is basically 7.5 kilonewton, so this is 7.5 kilonewton. So this, as you can see over here, 7.5 kilonewton, while the height of this other triangle is also 7.5, but this is negative 7.5, so this is in the negative region, so this is negative 7.5 kilonewton. So now we need to find the value of S, because we need to find the area of the triangle. So let's calculate the value of S. So what we're going to do is we are going to use similar triangle. So to calculate the value of S, it is going to be this triangle should be equal to this triangle. So it's going to be S, that is the width, divided by the height, which is 7.5 kilonewton, is equal to the width of the other triangle, which is 3 minus S. So this is 3 minus S, then divided by the height, which is also 7.5 kilonewton. So this is divided by 7.5 kilonewton. So what we need to do, we just need to cross multiply so that we can solve for S. So we're going to have 7.5 S. So this is 7.5 S, then is equals to, so we're going to have 7.5 multiply 3, which is going to give us 22.5. So this is 22.5, then minus 7.5 S. So if we move this to the right side, we're going to get 7.5 S plus 7.5 S, which is going to give us 15 S. So we have 15S is equals to 22.5. So if we divide both sides by 15 in order to solve for S, S is going to be equal to 1.5. So this distance is equals to 1.5. So if this distance is 1.5, then meaning this distance is also going to be 1.5, because 3 minus 1.5 is also 1.5. So now we know this distance. So this is 1.5 meter. So we can easily calculate the area of this triangle. So it is going to be, the area of this triangle is going to be 7.5, then multiply by 1.5, then divide 2. So 7.5 multiply 1.5 divide 2. This is going to give us 5.625 kilonewton. So I'm going to have 5.625 kilonewton. So this is the area of this triangle. So now we know the area here is 5.625 kilonewton, and we are starting from 0 because we don't have any external moment here. So we are starting from 0. So it's going to be from 0 to 5. Let's say 5.625 is located somewhere here, and this is positive because we're having a positive value. So it's going to be above the neutral axis, which is above the 0. So this is 5.625 kilonewton. So now what we need to do is we need to know how the curve is going to look like. How the curve is going to look like when we want to draw the moment. Is it going to be concave up or is it going to be concave down? How is it going to look like? So this is what I'm going to do. I'm going to show you a very, very short trick you can use to draw the curve of the moment, and you can use this for any type of beam you want to draw the bending moment of. So this is what I'm going to do. I'm going to show you the short trick, and it will look something like this. So let's say I draw a circle here. Then it's going to look something like this. So we are going to have, the first one is PG, we have an NI, we have NG, then we have PI. So what does this mean? So basically this is just a term I normally use. So I call this, please don't neglect infants, neglect deaf people only. And I'm not saying you should neglect deaf people. This is just the term I use to draw my moment. So please do not neglect deaf people. Make sure you always take care of deaf people. So what I mean by this is basically positive decreasing, negative increasing, negative decreasing, and positive increasing. So if we have positive decreasing, meaning our curve is going to look something like this. If we have negative increasing, our curve is going to look something like this. If we have negative decreasing, our curve should look like this. And if we have positive increasing, our curve should look something like this. So let's use this trick to draw this the curve of the moment. So as you can see over here in this triangle, as you can see, we are having a positive triangle, right? We're having a positive slope here, but it is decreasing. As you can see, it is decreasing. So meaning we have PD, positive decreasing. So because we have positive decreasing, meaning the slope is going to look something like this. So because of that, we are going to have something like this. So this is going to be the slope because we have positive decreasing. So now we are done with this. So the next area we need to calculate is this area, because in order to draw the your bending moment diagram, you need to get the area of the shear diagram. So let's take a look at this. So I'm going to draw this here. No need for that, you can easily calculate this. So the area of this triangle is going to be the height, which is 7.5 kilonewton, then multiply by the width. Like I said earlier, the width is going to be 3 minus s, which is 3 minus 1.5, which is also going to give us 1.5 meter. So 1.5 meter. So it's now going to be 1.5, then multiply 7.5, divide 2. We're also going to get the same value, which is 5.625 kilonewton. So, but this time around, it is going to be negative. As you can see, we're having a negative slope. We're having a negative area here. So we are going to have a negative value, which is negative 5.625. So we started with 5.625. So now we have negative 5.625, and these are in kilonewton meter. Sorry for this. This is kilonewton meter because we are dealing with moments. So this is kilonewton meter. So now 5.625 minus 5.625 is going to give us 0. So we are going to stop at 0. So it is going to be somewhere here. So this is going to be the value. So this is 0. So now we need to know the curve we are going to use to connect 5.625 kilonewton meter to 0. So all you need to do, you need to go back to this short trick here. So as you can see, for this part, we are having a negative area, and it is increasing from left to right. It is increasing, so meaning we have negative increasing. So if you take a look at this negative increasing, the slope is going to look something like this. So meaning it is going to look something like this. So we're going to connect this using this curve. So this is going to be the value. So here we are having a positive bending moment. So we're having a positive bending moment. So as you can see, we started from 0, we ended up at 0. So whenever you draw your shear and bending moment diagram, make sure that when you start from 0, you always end up at 0. If you don't end up at 0, meaning there is a problem somewhere, you need to check your work. So whenever you're drawing your shear diagram, you should start from 0 and you should end up at 0, meaning the areas should close up. Whenever your area does not close up, you need to check your work. Also for the bending moment, your area should close up as well. So as you can see, we're having a positive area here. So this is the bending moment. So this is how you can draw shear and bending moment diagram for this beam, and this is part 2. So in next video, we are going to be taking a look at part 3. So we are basically going to take a look at more examples. So don't go anywhere. Make sure you always stick to this lesson, and I promise you I'm going to try to cover all the necessary topics which you need to know to properly draw shear and bending moment diagram for beams. So like I said earlier, if this is the first time you are watching my videos, I make content concerning civil engineering, and if you are interested in that, please do not hesitate to click the red subscribe button and also click the bell notification icon so that whenever I upload a new video, you'll be the first to get notification. With that being said, this is all I have. See you in my next video. Bye bye.